So as promised, we're back to talk about now the regression equations, the linear equations that go with the correlation we talked about in the last section. So in this section, we're going to actually work on finding the equations for that linear relationship. We're going to discuss finding the equation itself, using the equation to predict influential points and outliers and how they affect the regression and what we should do with them. We're going to talk about residuals and residual plots and how to use those to analyze our correlation and regression results in the relationship itself. So the regression line is a collection, so given a collection of ordered pairs, that paired data, we're going to find the equation of the line that is the best fit. Now there are a lot of different types of regression line. There's a median line. There's just other regression lines. We're going to look at what's called a least squares line. And that least squares means the square of the errors of the residuals. And we'll define residuals later on. But if we square all the residual values and add them up, it's going to give us the smallest sum of the square residuals. And so when we talk about a linear equation, we're used to linear equations being of the form y equals mx plus b, where m is the slope and b is the y-intercept. If we're looking at a graph, if this is our line, so this is that value of b, and m is the rise for 1 unit of run. Well, in statistics, we use a little bit different form. We use y equals b0 plus b1x. b1 multiplies the x variable, that's our slope. b0 is by itself, that's the y-intercept. So both of the coefficients are b's, it's just b1 is the slope, b0 is the y-intercept. Algebraically, x value is often called the independent variable or the predictor variable, sometimes even the explanatory variable. It is the variable that is independent, it's free to vary as it wants, and we use it to predict the value of the other variable. So then y is the dependent variable. It is the one that's being predicted by x, and or the response variable. Its changes are in response to the changes of the x variable. So those coefficients, so what we are showing there is a regression equation for sample data. B0 is the linear regression for sample data. If we wanted to know for the population parameters, it would be beta 0. The slope of the regression line is B1, and again, for the population, it would be beta 1. So we're using this sample equation to estimate the population equation. Now remember, that is an estimate, it's based on our sample. If we were to select a new sample from the same population, we might get a slightly different equation. We probably will get a slightly different equation because hopefully we select different sample points. So the paired data, some of our requirements to do regression test is we're looking at the pairs, the ordered pairs that are selected must be a simple random sample from the population of ordered pairs. So the same requirement as we had for a correlation, and the other ones are the same as well. Visual examination must show that it is approximately a linear pattern in the data points. And because outliers have a strong effect, there can be no outliers. So if there are any points that are far away from the other points or that seem to break the pattern of the other points, we need to double check those to make sure that they're not mistakes. And again, note that these are sample data, so taking a different sample might get us slightly different numbers. So here, the requirements 2 and 3 are really checking one single requirement, and that is for the fixed values of x. The values for y are normally distributed. So that means for every value of that independent variable, there might be multiple cases where we have that value. The values that we would get for y, the observed values for y, form a normal distribution. And the center of that normal distribution should be our regression line. So our requirements, again, for the different fixed pairs of x, the distribution corresponding y values all have the standard deviation. So in other words, what that's saying is, if we have this is our regression line, the points should be equally scattered around that regression line all the way up through the points. If I have a set like this, if this is my regression line, and I have a spot where the points are really close to the line here, and then here all of a sudden they get really far away from it, and then they're close to the line here again, that's a problem. They're further away from the line at this point. I don't want to use a linear regression to describe that. That's a red flag. And so then the means also then lie for each value of x, the means of the different y values all lie along that same line. That's what we were saying before, is the values of y are normally distributed for a given value of x, and the mean is on the line. So finding the regression equation. The B1, the slope, is found by taking the correlation coefficient times SY, which is the standard deviation of the y values, divided by SX, which is the standard deviation of the x values. So we did this in the last unit. We found for this data set, we found I'm going to go back a sheet. We found the standard deviation here of the x values and the y values, and we found the correlation coefficient. So our value of B1 here is going to be found. Just click on the spot. It's going to equal the correlation coefficient right there times the standard deviation of y, which is this one, divided by the standard deviation of x. That gives us the point 17417. We had found that when we did our stat crunch. That was right here, the estimated of the slope, 0.1702. That's because we were using non-rounded values here. This is using a slightly rounded value, so we get the 174. We could also use an alternative formula. We had mentioned that one ugly formula for the Pearson correlation coefficient used the summation of the x times y's and the summation of the x's times the summation of the y's. Well, this formula here, B1, can also be found using those summations. So it's n, the number of data points, times the sum of the x times y values minus the sum of the x's times the sum of the y's, over n times the sum of the x squareds minus the sum of the x's squared. Let's show you how that works. Oops, get back there. So we're going to Excel here. We're going to go to this page where I got the summations in here. So my B1 is going to equal, on top, n is 9 times the sum of the xy's right here, minus the sum of the x's times the sum of the y's, close, divided by, on bottom it'll be n times the sum of the x's, sum of the x squareds, minus the sum of the x's squared. Notice, oops, what did I get wrong here? Let's just re-enter it. We're going to equal n times sum of the xy's minus sum of the x's times the sum of the y's, close parentheses, divided by n, which is 9 times the sum of the x squareds minus the sum of the x's squared. Oops, I see what I did. I just put the letter n in there. I got to change that to a 9. Let me try that again. So equals 9 times sum of the xy's minus sum of the x's times the sum of the y's. 9 times sum of the x squareds minus the sum of the x's squared. There it comes out. Okay, third time's a charm. So it is a little bit of a longer formula. It's easy to make mistakes. We get the 0.17417, exactly what we found here, using the standard deviations of the x and y and the correlation coefficient. But that is it's a little bit more complicated, but that is an alternative formula that you can use for that. Now the value of B uses the mean value of y and the mean value of x. It's the mean value of y minus B1 times the mean value of x. So let's find that over here. This is our mean, so B0 is going to equal the mean value of y, which is this value right here, minus B1 times the mean value of x, which is this value here, gives us negative 10.871. If I go to StatCrunch, so that was the value given right here, negative 10.871, the estimate of the intercept. That's the intercept estimate. It's really confusing here because the INT here stands for interval, or the standard deviation. So we want this is actually the intercept standard deviation and the slope standard deviation. Then there's an INT that stands for interval if I had selected different settings here. In this case, INT does stand for intercept. So we do get the values for our equation right there in StatCrunch as well. So what we did in our correlation to get the correlation coefficient of the 0.9473 also gives us the equation. So we're going to go through an example here of finding those values of B1 and B0. This is the data set we had before. Let's go through checking our requirements. So first of all, it is a simple random sample, so we're good with that one. We look at our graph, and yeah, these look to be approximately linear. Now, as I've mentioned before, kind of slightly curved like that. That might be a predictable pattern. If I wanted to be really strict, I might say, yeah, it might be better to do a polynomial regression than a linear regression here. But for this example, they're close enough that we'll describe them with a linear regression. Remember in the last section, we got that correlation of 0.94, what was it, 0.9473, whatever. So it's a pretty strong correlation. There are no outliers. There are no points that are way away from the others. So we're good with that requirement as well. So if I want to use Excel, they're talking about using Excel stat. I don't need Excel stat to do this in Excel. I showed you this in the last section. I just take these two sets. I'm going to go to Insert, Scatter Plot. Then I can just right click on one of the points and go to Add Trend Line. Linear, show the equation, show the R² value, and there it is. So first of all, this is the equation right up here. The 0.1742 is the slope, the negative, that is negative there, 10.872 is the y-intercept. And we talked about this R². I have to take the square root of that to get my R value, my correlation coefficient. So we can get it without Excel stat and Excel. I think that using just the scatter plot is easier than using the Excel stat added anyway. So we should know if the equation estimate is a true regression equation, if it's a good equation or not. Now we went through in the correlation section to talk about what is a significant correlation. And we saw the 0.947 is definitely a significant correlation for a data set of 9 ordered pairs. We should also double check this on the graph to see if it looks fine. What if we don't have technology? Well, we did that calculation. We found B1 using the correlation coefficient, the standard deviation of y over the standard deviation of x to get the 0.174 for the slope. And then we could use the equation. We did this in Excel, but we used the equation to get the y-intercept. So our equation is, now notice it's y hat and x, because the x values don't have the little hat thing over it because those are the actual values of x. Y hat is the predicted value predicted by the regression equation. So that's why there's the little hat symbol over the top of y. So y hat equals negative 10.9 plus 0.174x, where x is the size of the jackpot and y is the number of tickets sold that week, in millions, of course, for both of those. So now we need to check to see if that is a good regression line, we did the correlation check. Let's just subjectively take a peek and see. Looking at the data points, that line appears to fit the data points pretty well. In Excel, we've got the same graph here. Yes, that line, the dotted line, appears to fit those data points pretty well. So visually, a subjective analysis, it looks to be a good regression relationship, or good regression equation. If it's a bad model, we should not use it to predict. If we get a low correlation coefficient, or when we look at the graph, if it doesn't look like the points really align with the line, then we shouldn't use it. And if that's the case, if it's a bad model, if we get a low correlation coefficient that's not significant, the best predictor for y is y hat is just equal to the mean value of y. So for this data set, the mean value of y was 26.556. So the regression equation, the best regression equation would just be that y equals 26.556. There's no slope or y-intercept, it's just that y equals that constant value. In other words, there's not a great way to predict the y values. The x values cannot be used to predict the y values. A good model has that significant correlation that we found in the last section, and it looks like the points fall close to the line. So then we can use it to predict other values within the range of the data. So again, a good correlation, the coefficient will be between -1 and +1. The closer it is to 0, the weaker the relationship. So make sure we want those values to be close to either 1 or -1. It indicates the strength of the relationship. The scope, remember we had mentioned that if we got outside of this scope, like going out here, these points might take off like this, or down here they might vary away. They would be getting further away from that line. If we extended the line out, those points are no longer described by the regression relationship. So we want to keep our predictions within the range of the actual x values of the data. Now, some textbooks, and this is one of them, say you can go slightly outside of the range of the x values. How far you can go, though, is very subjective. It depends on the shape. Here, I would say we could probably go a little ways on the bottom side, but on the top side, I'd be leery because it looks like those points are starting to curve up. So I would say, no, we don't want to go outside the range of the data for this data set at all. So if we're looking at this, if we're trying to figure out what we can do to predict, if the regression equation is a good model, then yes, we can use it to predict values of y when we know the value of x. If it's not a good model, then, as we said, the best descriptor for y is that y hat equals the mean value of all the y values. And that's what they're saying here. It's just the average value of the mean value of y is your best predictor. So in this case, the jackpot versus the tickets is a good regression relationship. We got a strong correlation. The graph appears to be good. So we can use that to predict. So we might ask you, if the jackpot is $625 million, predict how many tickets would be sold. Now the predicted value is 90 million tickets using the equation. And we'll show you where that comes from in a little bit. Next, we want to say the second, this is not the data set that we had before. This is introducing a new relationship. Can we predict the IQ score for an adult if we know they're 175 centimeters tall? Well, looking at that, we'd say height should have nothing to do with IQ score. Short people can be geniuses as well as tall people can be geniuses, and the other way around. There isn't a good relationship there, so we can't use that as a predictor at all. So the good model, as we said, we've already found that the relationship between the jackpot and ticket sales is a good model, and it follows this equation. So we put the 625 in for x. We calculated that out, so I'll show you how that calculates out. So it's a negative 10.9 plus 0.174 times 625, and we get 97.85, or about 97.9 million tickets sold. The actual number of tickets sold was 90 million, so we're off by a little bit. The prediction was 7.9 million more, but that's actually fairly close to 90 million. So it's a pretty good prediction. The difference between those is actually something called the residual that we'll talk about in a little bit. A bad model, well, there is no relationship between IQ score and height. So the mean IQ score for the whole population is 100. So our best prediction of the IQ score for somebody that's that height is 100. The best prediction we have for the IQ score of anybody of any height would be 100. There is no good, valid relationship between height and IQ, so our only prediction is just take the average IQ of 100. So the paired results in the first question, comparing ticket sales to the jackpot, is a good regression model. So that's why we were able to use that equation. But the range of the data for those X values goes from 127 million to 334 million. If we had values that were outside that range, we would not want to try to use it to predict. We're going to stay within the scope of the data. So if we had a week where the jackpot was only 60 million, we wouldn't want to use this equation to try to predict the ticket sales. If we had another week where the jackpot was 500 million, again, that's way outside the range of the data. We would not want to try to use this model to predict. Marginal change, slope is a rate of change. And so the marginal change is the increase in Y for a change of X of being just 1 unit. So if the jackpot goes up by $1 million, what would we expect the change in the ticket sales to be? Well, that's just going to be the slope of the data. The slope is 0.174, or 174,000 if we convert it into millions. Every 1 million increase in the jackpot, we expect ticket sales to go up by 0.174 million. So an outlier is any point that is far away from the other data points. Now, there's another definition called influential points, and these are points that may be outliers or may not, but they strongly affect the graph of the regression line. So here's the original data set that we had before. Here's the data set with an extra point added. We're adding in the point of a jackpot of 980 million, but ticket sales were only 12 million. So you can see that point is way down here. That's way away from the other points. If I add that point in to the data and I redo the regression line, I get Y equals negative 0.0055x plus 26.692. Now, it doesn't show the correlation here, but I would say that the correlation coefficient probably gets really close to 0 here because there's only a couple points that are close to the line. These points are all way away from the line. But it actually took the line from even a positive slope to a negative slope. So it really changed the line. That's an influential point. Now, in this case, that influential point would also be an outlier because it doesn't fit in the pattern of the other points. We would go back and check to see if that was a mistake. Maybe there was a digit left out of the 12 million ticket sales. It might have been 112 million. Or maybe there was something going on that week that caused it to be low ticket sales. So that point is an influential point. Also, it's an outlier. We would check into it and most likely see if we can find a legitimate reason to remove it from the data, because with it in the data, it is not a significant regression relationship. So the residual is the difference between the observed value, the actual value, and the value predicted by the equation. The predicted value is that Y hat from the regression equation. So we saw that example where we had, let's go back a ways more. The predicted value, or the actual value, is 90 million for the jackpot of 625 million. The predicted value is 97.9 million. The difference there is the actual, the 90, minus the predicted. So this is going to be a negative 7.9 million ticket sales. So what that is saying is the actual value is 7.9 million below the predicted value, below the line, the regression line. And so let's use a simplified data set here. Let's get down to the right one. Here we go. Here's our simplified data set to talk about residuals. So this data set is described by the line Y hat equals 1 plus X. So that's this red line on the graph right here. This is our actual data set when x is 4 or x is 8, y is 4. So if the prediction, though, if I put 4 or 8 in for x, 1 plus 8 is 9, I get a predicted value of 9, which is the point on the line there. But x is actually 4. So the residual there is negative 5 because the actual value or the observed value is 5 units below the line. For x equals 12, well, 1 plus 12 is 13. This predicted value is 13. The actual value is 24. That's a difference of 11. It's 11 units above the line, so it's a positive 11 residual. The sum of the squares, the least squares model, means that we're going to take those residuals and square them and add them up. The least squares model should give the smallest number for the sum of those squared residuals. So let's talk about a residual plot. So a residual plot uses the equation and these predicted values, and it compares them. So I'm actually going to go to Excel here, and I'm going to make the residual plot. So what we're plotting is the x value and replacing the y value with the residual for that point. So I'm going to take this set of data, go to a new page, paste it in. Now I'll put my predicted value in here. So this is going to equal negative, what was that, 10.872 plus, go back here, 1.1742, 0.1742 times x. That's the jackpot value. So I get a predicted value there of 47.3118 million. And I do that for all of them. So this one would give me a predicted value of 11.25 million. So my residual is the actual value, so the ticket value, minus that value predicted by the equation. Oops, sorry, the other way around. Predicted value minus the actual value. So equals the predicted value minus the actual value. No, let me get myself straight here. I had it right the first time. It is the actual minus the predicted. So here the predicted value is 6.68 million, almost 6.69 million more than the predicted value. Down here we get that this one, the actual value is 7.55 million below the predicted value. So what I want to graph now is I'm going to copy these values here. I'm going to copy these values here. I'm going to paste special here. I'm going to paste just the values. And I'm just going to graph these two. So I'm going to go insert, scatter plot, and there is my residual plot. Now what I want two things. I want there to be no definite pattern. Now if you look really close, you might say, maybe it swoops up a little bit like that. But it's not really a definite pattern. And you want it so that the residuals are approximately the same size all the way along the graph. You don't want them to be way out there here, and all of a sudden get really close to the line for a ways, and then get way out there again. So back to my PowerPoints here. This is the residual plot that we got. Again, I'm seeing almost like a parabolic curve there, but it's not close enough to that curve to throw up suspicion. And because in the last section we got a really strong correlation value, we're going to be okay with this being a good regression relationship. So here, this graph here, the residual plot, is showing the points are equally spread out along the graph, no definite pattern. That is a good model. This next one here, the points seem to go in like a curve like that. That is predictable pattern. There's a pattern there. That is not a good model. So I would not want to use that regression equation to predict, since my residuals form that pattern. Now here, in this model, we can see the residuals all really close to 0 here, and then all of a sudden they get spread out. So the larger the x values get, the bigger the residuals are. That is also not a good model. So the residual plot is one of the ways we can analyze how adequate our regression equation is at describing our data. So you can see there's a lot of ways to double check. So we're looking at describing or double checking to see if we have a good to see if we have a good relationship here. One was to use the correlation coefficient. If we had that significant value of the correlation coefficient using that table A6, then it's a strong relationship. 2 was to look at the graph. With the regression line on it to see if it visually looks like a good predictor of the point. And then 3rd was to look at that residual plot. If that residual plot had that won't let me make it go away. There we go. If that residual plot had a predictable pattern, or if the points started getting closer or further away from the 0, then we know there's something wrong with that relationship. So there's 3 different ways to check up on our relationship to see if we have a good regression relationship. So that is it for correlation and regression. We'll come back next week to look at chi-squared testing.